Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on October 27, 2025, about 7 days ago. This paper shows that guiding 3D Gaussian splatting with language-prompted planar priors and multi-view geometric cues fixes textureless indoor regions, delivering high-fidelity surfaces with accuracy around 4 centimeters, F1 about 77%, normal consistency about 83%, and novel view PSNR about 26, while outperforming prior methods. The paper is titled PlanarGS, High-Fidelity Indoor 3D Gaussian Splatting Guided by Vision Language Planar Priors. And as we'll see later, the gains for indoor reconstruction are quite significant. Also, the author shared the implementation on GitHub. You can access the project there and check the README for getting started once it becomes available. It is the canonical place to follow updates, try the code, and look for usage guidance as the authors expand the repo. Alright, the repo link was shared before. Figure 1 presents the PlanarGS overview, which starts from multi-view images and language prompts and flows through the system to a room reconstruction. The green LP3 block produces planar priors from vision language segmentation, which then feed the yellow planar prior supervision with plane-guided initialization, Gaussian flattening, and a coplanarity constraint. The blue geometric prior supervision adds depth and normal cues. The gray column shows rendered color, depth, and normals that drive TSDF fusion to the final mesh. Okay, Figure 2 details the LP3 pipeline that turns language-prompted segmentations into reliable planar priors. The top row shows cross-view fusion, which transfers detections from neighboring views so missed walls and floors get completed across frames. The middle block adds normal inspection, using prior surface normals to split masks that accidentally merge multiple planes. The bottom block applies edge inspection with plane distance cues, so regions align with straight boundaries and result in cleaner, more accurate plane masks. Well, Figure 2 detailed how planar priors are formed. Figure 3 presents a side-by-side qualitative comparison across Replica, ScanNet++, and mu-shroom. The left columns show baselines like 3DGS, 2DGS, PGSR, and DN-splatter, which yield wavy walls and noisy geometry. The hours column displays flatter planes and sharper corners, so ceilings and floors stay straight. The rightmost column shows our colored meshes, which look complete and visually clean. So Figure 3 showed cleaner planes and sharper corners. Table 2 reports surface reconstruction scores on ScanNet++ and Replica, and the method leads across nearly all metrics. On ScanNet++, accuracy is about 3.9 centimeters, with F1 near 83% and normal consistency about 91%, surpassing DN-splatter by wide margins. On Replica, accuracy drops to about 2.8 centimeters, with F1 around 82% and normal consistency about 90%. These gains indicate both tighter geometry and smoother surfaces. So, while Table 2 summarized ScanNet++ and Replica, Table 1 presents mu-shroom results and highlights the gains. The method reaches accuracy about 3.95 centimeters with F1 near 77% and normal consistency about 83%, which signals crisper planes and cleaner corners. Novel view synthesis also improves with PSNR around 26.4, SSIM about 0.887, and LPIPS near 0.214. Baselines lag, for example, DN-splatter shows accuracy about 6.25 centimeters and F1 near 62%. Alright, the previous table covered mu-shroom scores. Figure 4 compares novel view synthesis, placing ground truth beside several baselines and the proposed method. The baseline renders show smeared walls and hazy edges, and the DN-splatter panel highlights a misaligned wall patch in the red box. The final column matches ground truth more closely, with crisp doorway edges and straighter tiles, because planar and geometric supervision suppress view-dependent artifacts. Wrapping up, 2 takeaways stand out. Language-prompted planar priors, fused across views, and geometric supervision together turn 3D Gaussian splatting into a reliable indoor reconstructor, with flatter walls, sharper corners, and stronger novel view synthesis. The broader impact spans AR/VR, robotics, and digital twins, since accurate rooms enables safer navigation and cleaner simulation. Thanks for listening. I am Alex, signing off.